Okay, next let's welcome paper ID 349, Kenglun Chang from Tsinghua University of China. The title of his speech is a semi-supervised framework for automatic pixel-wise breast cancer grading of histological images. Dr. Chang, please. Can you hear me?
Yes. Hi, everyone. Can you give me the permission of the sharing screen?
Wait a minute. You can try again.
Okay. Can you see the PowerPoint now?
Yes, I can.
Okay. So good morning, everyone. So my name is Kenglun, and today I am going to present our work for you, a semi-supervised framework for automatic pixel-wise breast cancer grading of histological image. So our team is from Tsinghua University and the Tencent AI Lab. So I will briefly go through the four-part background method and experiment result, and finally the conclusion. So in the background, so breast cancer is the most commonly diagnosed cancer for women, which is estimated to account for 30% of new cancer diagnosis and 50% of cancer deaths in United States. Early and precise diagnosis of breast cancer is crucial to improve the survival rate of the patient. The cancer effect can be observed in the whole slide image in the cellular and tissue level. So here we show an example of the cancerous cells distribution, which are classified into four categories: invasive cancer, in situ cancer, and benign, and finally the normal one. So so as we say, it is important to find out and classify the correct type category of the cancers, the cell. So recently, many computer-aided systems utilize the deep learning method to improve the classifications, consistencies, and accuracy. However, the robust deep learning model require large annotated dataset, which are costly to produce, especially for the medical image. Recent studies integrate active learning with deep learning, which utilize unannotated data to improve the performance of the deep learning method. For example, the fully connected network, FCN. But the drawback of the FCN is that it cannot be applied to the high resolution image, for example, a whole slide image. And there's another approach which are used to solve this problem as well. It is GAN. And it is mostly applied to generate the realistic image, which can overcome the limitation of the traditional deep learning models. But it has the problem that it will generate a subtle artifact on the original image, which will substantially alter the features of the cell and the tissue, and further mislead the model and affect the convergence of the parameter. And so to solve this problem, in this presentation, we propose a new semi-supervised framework based on the expectation maximization method. We leverage the unannotated whole slide image to adjust the deep learning model on a limited annotated dataset, reducing the reliance on expensive pixel-wise annotation. And our method can be has the below contribution. The first one is, to the best of our knowledge, we first apply the active learning method in the breast cancer grading, and the proposed method is based on EM method. It can effectively reduce the annotated dataset for the multi-class pixel-wise breast cancer grading. And secondly, we propose a sample selection method based on collaborative filtering, which select a credible and representative unannotated dataset for enlarging the training dataset. And we using the proposed semi-supervised framework, we can significantly enhance the performance on the pixel-wise prediction and achieve with only 30% of the annotated dataset. So our method is showing here the overflow of our EM model. So in a semi-supervised learning framework, we only have a part of the whole slide image that is annotated. We apply the initial CNN model to produce the probability map P, and then we normalize it to get a P norm. And then we use the EM algorithm to alternate to generate a consistent heat map. And then the fixed factor beta star is applied on the heat map to generate a class map as showing here. And finally, the most representative and credible patch will be chosen by the collaborative filtering and then to train in the CNN's next iteration. So totally speaking, the E step is here is the E step in the EM algorithm is for estimating the hidden label of the ZJ, and then the M step is for computing the optimal model parameter with maximized probability. And finally, we will use the result to select the page for the CNN to do the next training iteration. In the initialization part, we assume that all the page are follow the IID distribution, and we use the annotated dataset D to calculate our initial parameter, which using the argument we calculate the argmax and the product of the probability as the theta 0. And here we go to the E step. We base on the current parameter theta t at the T step of the EM iteration. We will calculate the probability maps P probability map P, and then we normalize it to get the P norm in a range of 0 to 1. We generate the class label C based on the beta start, and then we can obtain the final result of class map. The ground truth of the unannotated page is then extracted as a CJ, and the effective dataset will be chosen based on the page selection method to do the next iteration training. And the selection method that we use can be easily divided into two parts. The first is hard example mining, which is used for fully exploit the annotated dataset. And then it's collaborative filtering, which is used for extracting the suitable features. So here, the hard example mining is used in the initialization step to fully exploit the dataset, and especially those with wrong classification result. And effective coefficient alpha is defined here. The higher the value of the alpha is, and the harder the variable the corresponding patch is for the model to train. Here, for the collaborative filtering, in the E step, the page are selected using algorithm 1 here. So we will first apply the CNN to extract the feature of O page and then calculate the similarity between each unannotated data page, the unannotated page and the annotated page. Then we apply the majority sorting method here to above the compute page to determine the label of the unannotated page. If the assigned label is consistent with the PD1, and then we will insert the unannotated page to the ET, which will be used for the next stage training. Here, the CI denotes the class label of the page XI, and the P denotes the probability map. So in the initialization step, we first train our model on only 50% of the annotated data, and then we apply the model on the rest of the data to calculate the effective coefficient. And the page with the effective coefficient in the first quantile are selected to retrain the model. And finally, we come to the M state. So here, the CNN model is retrained on the effective dataset ET to produce in the E step. And the model parameter we are going to optimize is the theta t, which is the we use the maximize likelihood function. By inference, we can change it into the Q step, into the Q form as we show in the equation 3. And here is the final objective function that we are going to formulate. So in the experiment result, let's go through the data set. we use the dataset for training and validation from ICIR 2018 challenge. There are in total 400 image with about 15,000 times 1500 times 1500, which is obtained from the HME's stem breast histology microscopy. These images are labeled into the 4 classes, as I mentioned before, and each class contains 100 images. And there are 10 pixel wide label whole slide image that is much larger than 15,000 times 15,000. And finally, by cropping them into the same size, we can get about 6,000 normal patch and 600 benign patch, 300 institute patch, and 8,000 infected patch. You can see here it has a very long tail distribution of the dataset. And so the first step we have to solve this problem, so we have to do the foreground patch extraction to make the distribution much more uniform. So we extract the we use the high res so we display the result of the different method for extracting the foreground image. And the high resolution of the image we convert it into a gray image, and the intensity of the pixel of the circle wrap is about 0.76. As the OSTU method that drawback, it has the fail to extract a certain part of the tissue from the side of its complexity. And actually, so as you can see in the OCSTU method, it ignores most of the part of the cell on the top of the image except the middle one. So our method consists the variance between different cells and different types. So we can have a much more better extraction as shown in the third image here. And after doing the patch extraction, we can do the patch classification test. And our method can achieve the best result using only 30% of annotated dataset. And our neural network is a fine-tuned FGG19 network with the batch normalization. Given a large patch of with size of 1500 times 1500, we resize them into 512 times 512, and then we fit them into the network. For adapting to the fully connected layer, we add an average pruning layer, which convert the data map to a suitable factor size. The patch-wise experiment results are summarized here. We first apply the active learning method, LLM, which stands for LLM, to continually fine-tune the classification model with the informative and effective dataset. Instead of retrain the model with old datasets, so the 10% and 20%, 30% here refer to the different models training on corresponding portion of annotated dataset. FSL is a model trained on the full dataset. And our method with 10%, 20%, and 30% demonstrate our proposed method for using the 30% of the whole dataset can reach the best results. And for the experiment, the FSL method obtained 0.76 and 0.89, as you can see here. And our method can reach on 0.91 in accuracy, which is higher than FSL, which it can be referred from our unbalanced dataset distribution. So we will have a relative lower precision here. And also we extend our method to the pixel-wise classification. So to achieve this method, we first construct the heat map by the given whole slide image, and specifically, we compute the intensity matrix for each page by timing the theta t times the y factor. The theta t here is a fixed factor value that we generate by experience from the different type of the cells in the cell's density. And finally, we mapping the heat map from the cosmic by a factor of beta star, which is also a fixed factor. And As you can see, our method with 30% annotated data set can achieve the best performance with a score of 0.785, which is the best, which is much more better than the score of Quark and other set of our method. The three methods perform relatively well in detecting the large area of cancer. However, for small area of cancer, all of these methods usually fail. So we can see here as an example of the invasive tissue in A08 slides. It has a lot of small area cancer. Only our method can be successful detect them and classify it. Or on the other hand, FL's method is unable to recognize a lot of the small invasive tissue in both A02 and A08. In contrast, our BM-based method can detect them all and directly, which has reached a much more better performance. So in conclusion, the breast cancer is leading the cause of the female death, and the recently deep learning method cannot correctly classify it successfully. So we propose a EM model to approach this solution, and we can solve the deep learning dilemma, which is lack of a large annotated biomedical dataset. We reduce the reliance on the annotated dataset. We only use 30% of the training dataset, and we can trace the small cancers area successfully, and we don't have loss on the large area as well. So for the future, we will introduce more metrics and more parameter. For example, the maximum size of each cell, or the maximum size of maximum intensity of the different certain cell, to better fine tune our model. And that's all. Thank you for your listening.
Thank you, Chang. Thank you for your excellent speech. Is there any questions for Dr. Kenglun Chang?